Welcome, everybody. It is my pleasure to introduce our speaker today, one of our own, Professor David Timm. Although he's a native of beautiful Wisconsin, he made the right decision and came to school at the University of Minnesota in this department, where he got 3 degrees, Bachelor in Civil Engineering, Master's, and then a PhD in 2001. And after he graduated, he interviewed, I think a lot of people wanted to get him. And he ended up at University of Alabama at Auburn, that also, where also the National Center of Asphalt Technology is located, where he's a professor. He had a very successful career. He's one of the best known specialists in the area of pavement engineering. And he does a lot of very exciting work at the university, at the National Center of Asphalt Technology, the flagship of the asphalt industry in terms of research. He has many accomplishments. If I look at this list, outstanding faculty member, outstanding educator, knowing him, it's no surprise to see that. KB Woods Award for the best paper in the area of design and construction at the Transportation Research Board. And also as a graduate student, he got a very nice graduate fellowship from the U.S. Department of Education. He's going to talk about Road to Sustainable Future. This is in line with his research interests that include the pavement modeling, stochastic modeling of pavement processes, very, very interesting, and full-scale accelerated pavement testing. Please join me in welcoming Professor David Timm. And welcome back.
Thank you. Good morning, Skayuma. I try to say that in the deep south, and it's just, unless it's War Eagle or Roll Tide, nobody wants to hear about it. So it is really great to be back, and I think 2/3 of my PhD committee are in the room, so I hope we're not going to go back over any questions that I messed up from back in 2001. But it is a pleasure to be back, and it's interesting getting to spend some time on campus. And Mihai, thank you for all your hospitality. Spending time on campus, and some things are, I don't recognize, and other things are just the same. In this room, there's been some upgrades, but it's about how I remember sitting maybe about where Professor Galambos is, learning structural analysis from him, and from Dr. Barnes learning computer applications. So I have a lot of fond memories, and I'm really honored to have been invited back, and I'm really thrilled to be here. So what I'm going to talk about today is some research that I've been working on really since I was just about ready to leave the U, and really it's kind of been sort of a path I've been on in my research, is looking at what we call perpetual pavement design, or long life asphalt pavement design. And this is something that the industry has been really keen on since about 2000, and it was one of those things that the industry got very excited about it, and they developed a lot of marketing, and they didn't really have the research yet to really, and you've maybe heard that story before, putting the cart before the horse. And so what I'm going to kind of go through today is some of the design philosophies that we've developed, some of the findings we've had from our NCAT test track, and how that's kind of worked its way now into engineering practice. So before I do that, I kind of want to provide a kind of a global picture here of our roadway infrastructure, and maybe play a little game here for just a minute. But the CIA tracks just about everything, and one of the things they keep track of is how many miles of roadways we have on the planet Earth, and maybe at some point in the future they'll track it on the moon and Mars and wherever else we end up going. But at the moment, not at the moment, as of 2013, there's nearly 40 million miles of roads on Earth. It turns out as a species we're really good at road building. And it's enough roadways to circle the Earth 1,600 times. So there's a tremendous amount of infrastructure in terms of building. Every civilization has had roads. I mean, going all the way back to kind of prehistoric times and Native Americans and all around the world. It's just something that we do. We have to get from point A to point B. And I pulled up the top 5 list here. So anybody have a guess, number 5 on the list in terms of roadway mileage? No guesses? Russia. Well done.
You told them.
I didn't tell them. Think about the landmass of Russia, and number 5 on the list there, but think about that land mass in comparison to the numbers we're going to get to here. Number 4 on the list? You've done your duty. You're a ringer now. Number 4 on the list. 2 for 2. Well done. Okay. So Brazil, all right. How about number 3? If we run the table, I'll be really impressed. That's pretty good.
Yeah, China. I think it's China.
China. Now look at the order of magnitude there, right? Getting into some, and China, by the way, is growing. You all know this. The infrastructure investment is tremendous. I've had an opportunity to work some in China, and it's mind-boggling. We would go 1 year, and we'd come back the next year, and they'd say, well, we built 600 kilometers of expressway while you were gone. You know, in 1 year. And it's a tremendous amount of road building going on. And they recognize the need to move people and goods around their country efficiently as a key to economic success. And 2.5 million miles. How about number 2 on the list? Japan? No. No. India. A lot of infrastructure there. 2.9. Number 1 on the list? U.S. And it goes up quite a lot. Again, let's kind of look at the order of magnitude here from Russia up to the U.S. You know, some economists cite the fall of the Soviet Union in part due to the kind of the poor infrastructure that they had. So we have a lot of roads, and in the U.S. we're often looked at as having sort of the model road network. And in the U.S. we have 2.6 million miles that are paved. 90-something% of that are asphalt pavements, and about 1.4 million miles unpaved. And just to give you a little insight of to where I'm at now, Auburn University, this is Atlanta, Georgia, here, and this is Montgomery, Alabama, and we're kind of in between there, just off of I-85. So we're about 100 miles southwest of Atlanta. Definite climate change when I left here and moved there. You have to get used to the heat and humidity as opposed to the cold and the snow. But we have a lot of miles of pavements, and again, we're looked at as a model. But if you ask ASCE how we're doing, and many of you know this, our grade isn't that good. The last grade that came out was in 2013. We got a D for our roadway network, and there's a few details in here I want to pull out. And the first is that it's estimated that we waste $101 billion a year in fuel, just sitting. Construction zones, car wrecks where you have congestion, that kind of thing. And there's just a tremendous amount of wasted time and fuel. That doesn't even begin to count the environmental impact. Think of all the CO2 that's being pumped into the atmosphere and nothing is being accomplished. It's very wasteful. And the other thing I'll pull out of there is that FHWA estimates that we would need $170 billion more dollars to go into our infrastructure to bring this up to an A grade. I think many of us would be happy if we just got to a C, right? C's get degrees. If we got to that point, that'd be good. But, you know, we just finally got a long-term transportation bill passed, finally, after so many years of patches and that kind of thing. And the funding outlook still isn't very good. I mean, John, I don't see a big smile on your face like everything at the DOT's suddenly turned to gold, right? It's the name of the game is still do it cheaper, do it faster, do it for, and make it last longer while you're doing all that. So that's where we're at. What about how expensive is road building? It's pretty darn expensive. These are some data from ARTBA, American Road and Truck Builders Association. If you want to build a new 2-lane undivided road in the U.S., you're looking at $2 to $3 million per mile. In an urban area where you've got to deal with right-of-way and you've got to deal with maybe moving utilities and that kind of thing, you're looking at $3 to $5 million a mile. It's very expensive, and the numbers are going to get worse as we go down this list. Go to a 4-lane highway, $4 to $6 million per mile in a rural and suburban area, 8 to 10 million in urban setting. 6-lane interstates get very expensive, $7 million per mile in rural, $11 million per mile in urban. The Georgia DOT recently, outside of Atlanta, was expanding a section of interstate that's kind of what used to be on the outskirts of Atlanta. And they spent $117 million in 7 miles. They were raising bridges, this kind of thing. They built a CRC pavement, very expensive to do that, and it didn't solve really any congestion problems. It just moved it a little further out and allowed people to live further away from the center of the city. So it's very expensive. Obviously, it's not terribly sustainable. If we want to rebuild these millions of miles that were many of them built in the 1950s and 60s, it's very difficult to have the kind of political motivation, the funding sources to support that kind of effort. If you want to expand, you're looking at about $4 million per mile. And the last one on the list is actually the cheapest of all these options. And really it applies to our current infrastructure. To mill and resurface a 4-lane road, okay, so if we have an existing highway pavement 4-lane road, so we're kind of talking about maybe this, we're looking at about $1.25 million per mile. It's not cheap, but of those options, and given our existing infrastructure, it's the one that is really most economically viable. Now, in order to make this work, this has to be a successful rehabilitation strategy. If we have a tremendous amount of cracking and we're just milling the cracks and they're still underneath the pavement, that hasn't really fixed anything. We're doing that every few years. So we need a strategy that is a true fix, and that's kind of where I'm heading with all this, is trying to get to a point where we get into this kind of an operation and we can mill and resurface as opposed to reconstruct. Reconstructing pavements is very, very expensive. So where are we on the evolution of pavement thickness design? Before the 1950s, and at the NRRA conference yesterday in St. Paul, there was a lot of discussion, a lot of great old pictures about old road construction and pavement design and so on. But before the 1950s, it was really experience-based. There wasn't a design methodology that you would follow to design a pavement. There's just some experience, mostly geotechnical engineers, and their knowledge would design a pavement for the soil conditions. In the 1950s, we had the Interstate Act and this need, again, putting the cart before the horse. There was money and a desire to build an interstate network, but there wasn't a design method to do that at that point in time. So we're going to build this massive highway infrastructure, and we don't have a design method to follow to make sure that it's going to last for many lifetimes. So in the 1960s, there was a road test, the AASHTO road test, many of you heard of before, and that is where the development of many empirical models came from, and they're just statistical correlations between how thick the pavement ought to be and how heavy the trucks are. That's all it is. They look very complicated, but it's just a big statistical equation that is useful to scare undergraduates with. Next up were the development of mechanistic-empirical models in the 1980s, and the idea of tying pavement mechanics, calculating stresses and strains, to pavement performance. And then in the 1990s, and when I was in school here, we got into working with Minroad and really looking at developing mechanistic empirical design as a design tool, developing those kind of philosophies and so on. And that was kind of the focus of my master's thesis, was kind of incorporating reliability, and Professor Galambos was a huge help in doing that, incorporating reliability ideas into that design method. And so as that was going on here on a national basis, they were developing what was supposed to be called the 2002 Design Guide. It was the new AASHTO design procedure, and that 2002 became, now it was just released I think a year or two ago for commercially, so it was much longer time horizon. And where many states are operating right now is looking at trying to implement these procedures. Minnesota isn't one of those states. They have their own method, the MinPave system, that I don't think they're going to be switching from that to the national system. So that's where we are, and what I'm going to get into is kind of perpetual pavements that fits in kind of on this end of the spectrum. So as you look across the U.S. at kind of the state of pavement design, it's a patchwork quilt. There's not a uniform, you have many states doing many different things. All the states that are in gray are using the old AASHTO empirical method, and Alabama's one of them. We're using the 93 design guide. State of Georgia is using the 1972 design procedure, kind of outdated. There's 11 states that are making the transition where they're using both empirical and mechanistic empirical. They're running design side by side, which I think is a good idea. The state of Indiana went whole hog and they said we're going to drop our old system and do the new, and they had some growing pains that came along with that. Minnesota and Illinois and Alaska all have their own design systems. And in fact, if you go all the way back to just after the AASHTO road test, Minnesota has had its own granular equivalency design approach, and they now have their own mechanistic empirical design approach called MinPave. So it's a patchwork quilt, and some states may never implement the new design system. This is if we talk about the existing AASHTO design equation, this is it. And it looks complicated, but it's really pretty simple. There's 5 inputs to it. You have traffic, a Z statistic corresponding to reliability, a variability term on your inputs, a change in serviceability or expected performance, and a soil strength measurement or quantity here. You put all that in this equation, and then you back solve it for the structural number of the asphalt pavement, and that gives you the pavement thickness. So just 5 inputs will give you an asphalt pavement design. There's a lot that goes into it, but pretty straightforward. The new ME design system has hundreds, if not thousands, of inputs. Things like shortwave absorptivity of the asphalt, the thermal conductivity of the granular materials, all kinds of things that feed into all the different models. It's a very data-hungry design approach. But this is where many states are currently designing at, is using this AASHTO 93 approach. And its day is kind of come and gone. AASHTO no longer supports it. There's a lot of kind of spreadsheet programs and kind of rogue programs out there that'll solve this, and many states are just wanting to maintain it. And the reason that it's kind of seen its day is that all of these terms that you see in this equation are just regression coefficients. You don't see stress, strain, deflection anywhere in there. You don't see a prediction of cracking, rutting, faulting, or anything. And so the question is 9.36, for example, applicable for our conditions today? And the answer is probably not. You think about where it was built in northern Illinois and the kind of asphalt plants and construction practices that they used during the road test, that 9.36 and all those other terms are kind of tied in to those conditions. It was just a big experiment. They had very specific traffic and climate. For here, maybe it's pretty applicable. For where the part of the country I live in, it's not applicable at all. We don't have thermal cracking. When you see this going on, that's when you go to the store and get all the bread you can possibly fit in your car and go home for a few days, because Armageddon is upon us if we see that kind of weather condition. This was a set of design curves that were published in 1962 that shows the relationship between pavement thickness on this axis and the number of load repetitions on this axis. And it was meant to be just a very simple representation of how to design an asphalt pavement as a function of different types of axles. Like this top one here is a 30,000-pound single axle, down here is a 2,000-pound single, and just showing the influence as you have more repetitions of traffic, you end up having to design more or a thicker pavement. So that makes sense. What kind of got lost in the shuffle between 1962 and everything that's come since then is that this graph has a tremendous amount of extrapolation going on. Okay? All of this to the right and all of these shaded areas, those are all extrapolations of those design curves. There was really not very much that was interpolated, or that, most of our design conditions today are not interpolations, they're extrapolations. They only applied 1.1 million load repetitions on that road test. So anything above that is an extrapolation. And these curves really have no end, right? They just kind of keep going. There's not an upper bound to that. Pavement designers will tell you, well, I think, we get to 20 inches of asphalt, that probably ought to do it, okay? The design code, however, doesn't have any natural cap in it. It just, you put in more easels, more traffic, it just keeps increasing indefinitely. And that's a problem, because we don't have the money. It's not sustainable. We don't have the money to support that kind of road building. And there's some projects in Indianapolis. There was a 400 million easel design, and they did the design. It said 26 inches of asphalt. The I-710 in California that was rebuilt back in the early 2000s, it was a 200 million easel design. It's supposed to be 20 inches of asphalt. doesn't make sense. And it's just the design code. It was never really meant to be used in that fashion, but that's what we have. That's the current national design standard. So enter then this whole idea of having mechanistic-empirical pavement design. And what is kind of embedded within this whole design system is really bringing the engineering back into pavement design, not relying on statistical correlations, but actually computing stress, computing strain, looking at how that is a predictor for cracking, rutting, the other kinds of distresses. This is a trench that we cut open at our test track, and you can see a lot of rutting up top here. This is a mix that the state of Missouri provided to us. And one of the nice things about the test track, of course, is we can kind of think outside the box, try risky things that on their road network would be catastrophic. At our test track, we learn a lot, and maybe if it doesn't work out, you know, it's fine, it's not a problem. So in this case, we had some rutting of the pavement. You can see it's a pretty thick asphalt pavement. We've got our typical buildup at the track is this, you know, layers of asphalt, and then granular base layer, and then the soil down below it. But kind of the core concept of ME design is that you think about the pavement cross-section and you define its layer properties and the thicknesses of the layers. And we typically use layered elastic theory. So Hooke's law and everything's linear, springs, and you know, there's no permanent deformation, although you can see obviously there is. But within the modeling part of it, we just assume everything is linear elastic. That's kind of where the state of the practice is. So we have to define the Young's modulus of the materials. And then we simulate load events going over the pavement surface, okay, and they can be variable. Obviously, on an open highway, they will range in magnitude, tire pressure, axle spacing. There's a whole spectrum of loads that the pavement is going to see. And we then, using our mechanistic models, like we use the Westleya program quite a lot, we can make predictions about the state of stress and strain inside of the pavement structure. So under this set of conditions and this load on this day, we can simulate how much strain we're seeing here and how much, or tensile strain we're seeing here, how much vertical compressive strain we're seeing there, and then link that to how much rutting we're going to see or how much cracking we might see. And so we have to calibrate, and that's the empirical part of this design system. And so that's kind of the essence of ME design, and what the new design approach is about is making these computations of load events on top of pavement structures. And it gets way more complicated because as soon as the temperature changes, all these material properties change. Vehicle speed changes, the asphalt responds differently to that, and so you get a different response from that. But it essentially boils down to this: is pavement structure, simulate a load event, calculate stress and strain, correlate that to performance. And the new design software that AASHTO, if you're interested, do you have a copy here, Mihai? No? It's $5,000 a year for this software. So we have one copy at NCAT. It's in a locked room behind a locked door, that whole thing. But it's a very expensive piece of software, and it does that kind of analysis. And it has really complicated models in it. It'll simulate frost movement through the soil, moisture movement, do all kinds of things. And at the end, you get an analysis of your pavement about how it's going to perform over time. The tricky part about it is that because there is an empirical aspect to it, it requires calibration. So the plot in fact, it involves a three-step process. First, you have to evaluate what was done nationally. Does it meet or fit your conditions? If it doesn't, you need to go through a calibration process to remove the bias and remove the error. And then when you're done with that, you have to check it and see if I feed it some new pavements, what happens? Does it accurately predict that? And this kind of conceptually is pretty simple, but in practice, these are multi-million-dollar, multi-year studies that are going on all over the country to try to calibrate and locally deploy this design system. So what's happening in these graphs here, this is measured rutting on the x-axis, predicted rutting in the wheel paths on the vertical axis, and the left graph is the kind of using the national calibration. At our test track, we're running trucks, we measure all of our inputs very carefully, and then we can look at measured versus predicted, and you can see that there's a lot of bias in that prediction. It's over-predicting rutting. If we were to just use the national calibration, we would over-design our pavements because it tells us that we're getting more rutting than we actually are. And so we go through the calibration process and adjust the calibration coefficients to try to recenter some of the data, as you can see here, okay? So that's kind of where we are with ME design. Again, many states are working on this. The fundamental problem with that still is that for some reason, we still design pavements to fail. We design them to have terminal amounts of cracking, certain area of cracking on an asphalt pavement or so many slabs cracked. We don't design many civil engineering structures to fail, right? We usually look at what the limit is and then try to come in below that limit, and then it's catastrophic type things that lead to failure, not just the routine application of traffic. And because of that, we are in this kind of endless cycle of having pavements that fail that need to be reconstructed. And it's, as I showed earlier, it's very expensive to do that. So that leads us then into this idea of perpetual pavements. And the idea being that if we were to, again, think about those stresses and strains, but build the pavement thick enough that we operate below what we call the endurance limit of the materials, we wouldn't have cracks that initiate at the bottom of the pavement and propagate to the surface. When that happens, it's really game over. You can't really, you can seal it, you can try to overlay it, but it's a Band-Aid. It's not a true fix. So the idea is to build it thick enough, and this is really over thick. This was a cross-section at our test track that was purposely built very thick. This is about 30 inches of asphalt here. And we were looking at just the performance of the top few inches. But the idea is to try to build it just thick enough that you wind up with only distresses at the very top of the pavement that we can mill and inlay, and again, that's the most cost-effective, most sustainable option. We can even take the material that we've milled up, reconstitute it, and put it back down. It's 100% recyclable. So that's, again, a very sustainable option. So a perpetual pavement, there's actually an award program, and Minnesota leads the country in winning these perpetual pavement awards. The Minnesota Asphalt Pavement Association has been very active in promoting this concept, and Jill Thomas, another graduate of this program, is the director of MAPA, and every year, I think every year there's been an award, Minnesota's gotten one, going back to 2000. So they lead the country, or you all lead the country in these awards. And the definition is that they have at least 35 years of service. Many of them have 50 or more years of service. Minimal structural improvement, so not, it's not like we built the pavement and then added 6 inches. There's a 2-inch per time with a certain interval between overlays. So minimal structural improvements, and then no deep structural distresses. So if we don't have deep structural distresses, any problems we see in terms of the wearing surface, or maybe we have a friction problem, maybe the aggregate has started to polish, we can easily and quickly remedy that at the surface of the pavement. And that is, that can be done overnight. Mill up a length of road and put down the new riding surface, and we'd hardly even disrupt the public. These are all award winners. All the green states here, and from Alaska to Florida, have every climate. We've identified these kind of roads that have lasted a long time. Last year I was in Oklahoma, and there was a subdivision that had been built in the early 60s, and they won a Perpetual Pavement Award. It was not even a very thick pavement. It's just been there forever. They haven't done anything to maintain it. Great condition. Okay, very cost-effective pavement. So the goal is to design so you don't have any deep structural distresses, prevent bottom-up fatigue cracking. These are the two big ones, bottom-up fatigue and structural rutting. All distresses are quickly remedied from the surface, and this will give you what we call a perpetual or long life. The picture is one of our trucks at the track. They run 16 hours a day at our test track, 2 shifts of drivers. For the students in the room, stay in school. You don't want to be driving trucks at our track for the rest of your life. They log about 26 laps an hour. As a team, these 10 drivers drive about 1 million laps around our track in 2 years. Tremendous fatiguing environment. Talk about fatigue. And they're hauling these triple trailer sets, and they drive on these test sections, and we're applying about 10 million easels in 2 years of time at the track. So we're trying to prevent this bottom-up fatigue cracking where we get tensile strain here, initiates and propagates a crack to the surface. Prevent, and I'll reuse this picture, deep structural rutting where we have rutting through all the layers and even down. You can see here above the string line, you can see some movement of that aggregate base. When that is happening, that is not a perpetual pavement. That's, to fix that, we really need to go down, remove, replace, and rebuild. Perpetual pavement is to, again, we don't want to see those distresses, so we want to identify, well, how far can that asphalt stretch or bend before a crack would initiate, and design below that. Okay? A Likewise, down in the underlying materials, how much vertical strain can it sustain before we have plastic deformation? And then design, it's like an allowable stress design, right? Design at some percentage of the strength or the resilience of the material is what we're trying to do with this design approach. So this is a slide that actually Dave Newcomb, some of you remember him, put together related to perpetual pavements, but really it's meant to kind of identify that in the surface of the pavement we have to be cognizant of high shear stress and strain, vertical compressive stresses that contribute to rutting, so we need to have high modulus rut resistant materials there, and then have fatigue resistant materials at the bottom of the pavement that can withstand that kind of bending action as the loads are going over, it's bending like a beam, and we want to make sure that we can resist that. People are putting high polymer content asphalt into these layers, designing at lower air voids to give you higher asphalt contents, all kinds of strategies to develop more fatigue resistant materials down in those layers. So ME Perpetual Pavement Design looks just like kind of the schematic I had earlier where we define a pavement cross-section, simulate loads on the pavement, calculate pavement responses. But what's new is that we recognize that the material has a lower bound and endurance limit, or what we call the threshold strain, and we can measure and have measured this in the laboratory. That you get down around 100 microstrain or so, and you can bend that beam forever, kind of like a coat hanger, right? If you bend it just a little bit, it's not going to break. You get it above that endurance limit, it'll break in a few cycles. Recognizing where that is then has a profound impact on how we design pavements. If we're above that endurance limit, well then we'll have micro cracks that form and can propagate to the surface. But as a designer, we want to operate just below that endurance limit, and that will give us a perpetual fatigue life, for example. So with that kind of design philosophy in mind, as part of the work I've done at NCAT was to develop a couple of computer programs. And the first one here, Per Road, this is really, some of you remember Rodent. I don't know, Vaughn, if you remember that program that we developed a long time ago, but it was a mechanistic-empirical pavement design procedure that we called Rodent. Dave Newcomb came up with that name, Rodent. It had Goldie Gopher on the title screen and everything. It was awesome. And that has morphed now into MinPave. So it kind of went down the MnDOT road, became MinPave, and then we took it the other route and turned it into a perpetual pavement design program. And the program does multi-layer linear elastic analysis. We have Monte Carlo simulation is within the software, so it'll take all of your inputs and simulate the variability of the inputs and the impact it has on the output. And we can use that the industry uses it for perpetual pavement design. And then we also developed what we call Per Road Express, which is kind of a simple one-page, more like a county or city engineer would use if they're doing a subdivision street. They don't have the time or resources to develop the inputs they need here. They maybe just have an estimate of traffic, maybe a soil classification, and a couple other inputs. They can get kind of a quick and dirty perpetual design from that. And so these are being used by the industry, and there are perpetual pavements that are being designed and built around the country. This research has also taken me to China, where we did a perpetual pavement experiment in Shandong province back in 2005. And it was really exciting to see them change their design code. And when I mentioned the 600 kilometers, I was kind of shocked when I came back and said, well, we have a new design and we built 600 kilometers. We hope it works, kind of thing. And it did, thankfully. This design approach is being used now. The Australian Asphalt Pavement Association is promoting the use of perpetual pavements, and we're working with them to help kind of develop their design system. So let me now get into some actual data and talk about the NCAT test track. So this is our track, and many of you know in the South it's NASCAR country, and we can't help but build oval tracks for trucks to run around on. So this is 1.7 miles around, and in the curves it's a 15% embankment to carry our trucks around the curve. Every 200 feet we have a new test section. So sponsors come to us and say, hey, we want to look at whatever, perpetual pavements for example, and we build them test sections, and then we put 10 million easels on in 2 years, and then we turn around and give them the results of whatever that they're investigating. It's a cooperative experiment. We have many state DOTs, corporations. Shell Oil Company has sponsored work at the track. Trinidad Lake Asphalt has sponsored work at the track. And DOTs as far away as Texas and as far north as Indiana have sponsored work at the track, although we now have a partnership with MnDOT And we're partnering with Minroad, and so we're kind of covering the entire temperature spectrum now, which is really exciting. So I'm going to talk about briefly 2 different perpetual pavement experiments. One of them was kind of by accident. That was this one, N3 and N4. This is our north tangent, and so they have an N and then the cell number. So N3 and N4, and then this was an intentional perpetual pavement experiment at the state of Oklahoma sponsored to look at kind of the cost effectiveness of building these thicker pavements. So experiment 1, N3 and N4, they were both 9 inches of asphalt concrete over our kind of typical dense graded aggregate base on top of the soil. And they were designed in 2002 to last 10 million easels, kind of one duration of our loading. And they were designed using the 1993 AASHTO design guide, that old equation that I showed earlier. And we were kind of surprised. We made it through the first test cycle and the pavements didn't show any cracking or rutting. We talked to our sponsor, ALDOT, Alabama DOT, and they said, well, let's see what happens. Let's put another, so they left them in place. We made it to 20 million, same story, made it to 30 million. 3 times the traffic that they were predicted to carry, they carried. At that point, they said, well, we've learned what we're going to learn from these, we're going to take them out of service. But they were, by all accounts, acting as perpetual pavements. And you know, we're not talking about 26 inches of pavement, we're talking about 9 inches of pavement on what was a pretty good pavement foundation, which was important as well. So we were able to kind of get a lot of information out of these pavements that helps us understand better how do perpetual pavements kind of fundamentally behave from a structural standpoint. We operate a pretty aggressive falling weight deflectometer testing program at the track where we have this, some of you are maybe familiar with this, but essentially have a vehicle that has a load set back there that we drop a weight on the pavement and we measure the deflection and we can use the deflections to determine what the properties of the layers are underneath the pavement. And we test all over these test cells. And what we're able to do then is back calculate the layer properties. And what we have found in these 2 pavements is that, and if you think about sort of the in-place stiffness of the materials, the modulus can do one of 3 things in a real pavement. It's either going to go up, it's going to go down, or it's going to stay the same. If it's going down, right, it's kind of like the stock market, right? That's the 3 possibilities. Sometimes it does all 3 in 10 minutes. So if it's going down, that's a sign that we have cracking occurring probably, or damage is accumulating because it's not able to carry that load as effectively and the stiffness is decreasing. If it's staying the same, that means probably it's structurally healthy, and if it's actually aging over time and that binder is stiffening, what we'll see is an increase in the modulus, and actually that in turn gives us a reduction in the strain level. So what these are showing is from 2 different test cycles, 2003 and then 2009, the modulus of those in place, or the modulus of the materials in place. And so between 03 and 09, we had a 12% bump in that modulus, got better with time in terms of stiffness, and then 03 to 09, those 6 years on this section increased by 20%. So that's a clear indication that there's not damage accruing or accumulating, and actually it's increasing modulus over time. In turn, the strain at the bottom is decreasing. It's getting better as we go along, and that's a good thing. Performance, we have an ARAN van that drives around the track and measures rutting. And this is the kind of what we would call failure, 1/2 inch or 12.5 millimeters. And this is 3 test cycles worth. So 0 to 30 million easel, or from 2003 through 2011, we topped out at 8 millimeters of rutting, which is very good performance. If you're around 1/4 inch or less, that's very, very good performance, especially on pavements that we didn't expect to perform this well. So excellent rutting performance. If we look at how smooth the pavement was, this is the International Roughness Index, so sort of the up and down movement of the vehicle as a function of it driving forward. This is what we would call failure, and really they didn't change too much over time. Very smooth riding pavement. Again, that's a good thing to see. We did identify, so this is how we detect cracks in the south, by the way. Crawl the pavement. We call it the biocular neural network crack detection system, right? 2 eyes and a brain will detect a crack. And you wouldn't know it, but that pavement surface right now is probably about 140 degrees as he's crawling, so he's wearing knee pads and gloves. But he's able to detect cracks when the high-tech cameras can't catch, kind of thing, and he's able to detect those cracks very early on. So what we're showing, this is a map of the test section. Traffic's moving from right to left, and we saw some cracking here in section N3 and some cracking here in N4. And so naturally, when we decided to take them out of service, we said we got to cut them open and see, is it, if it's bottom up, it's kind of game over. We can't call it perpetual. If it's top down, then that's behaving as a perpetual pavement should. That eventually you may see some top down cracks as the pavement ages become stiffer and so on. And so N4, this is a trench we cut, and it doesn't show up very well here, but there's no cracking here at all through those cracks that I showed on the map. We did identify a crack right here that came from the bottom in section N3, and I'll highlight it and go back and forth. You can kind of see it. Okay. Now what happened, and some of you maybe can see this a little better than others, but there's also a purple cable sticking out of the pavement. There's right where we put a sensor. Right? And so people always ask me, how did you know where to put that sensor, right where the crack was going to form, right? So obviously it's probably a weak spot in the pavement due to our instrumentation activities in that area. And so we attributed, I think safely attributed that to have been a disturbance. We didn't see cracking anywhere else in the section than right over where that sensor was. Okay, so we also embedded strain gauges in the pavement. We measure the kind of the in situ strain over time, and we can look at the cumulative distribution of strain. And what I've got here is the cumulative percentile and the microstrain here. And so, for example, the 50th percentile strain for the two sections was around or just under 200 microstrain. Now, while we're doing all this testing in the field, we also have these same mixes we take in the laboratory, and we measure all kinds of properties, but one of the things we measure is where is that endurance limit? What is the strain level at which below which we don't have cracks developing? And in the laboratory, that came in at about 150 microstrain for both of these materials. One was polymer modified, one was unmodified. And what's interesting is when you put this number together with these distributions is that about 65 to 60% of the time we are in excess of that endurance limit. Okay, lots of differences between lab and field. In the field, we have temperature cycling, we have rest periods between trucks, wheel wander. In the laboratory, it's a beam of asphalt, and it's flexing at a constant temperature and no rest periods, that kind of thing. What this tells us is that if we design for 150 microstrain, it's going to give us a conservative design, because clearly we can sustain much higher strains and not have that bottom-up fatigue cracking. In fact, what we developed was kind of a lab-to-field ratio of about, at the 90th percentile, designed at about 2 times the lab endurance limit. So if your laboratory number is 150, designed at the 90th percentile strain at 300. Okay, this is where in the per-road software all the Monte Carlo stuff comes in, because we can feed in uncertainty about the materials and the loadings and so on and generate distributions of strain, and we can compare it against, say, a control distribution like this and use that as a basis for design. So this was just for these two sections. We said, well, if we saw that here, what about all of our other sections? Some have cracked, some haven't cracked. If this is going to hold true, maybe we ought to see a difference in their strain distributions. And so this is a whole bunch of different test sections from the track. Again, cumulative percentage, microstrain. And what we found was that everything on that red line or to the right had bottom-up fatigue cracking. Everything to the left, on or to the left of that green line, is no fatigue. And what's really interesting is that, down here there's kind of everything is mixed and crossed over and so on. But at about the 60th percentile or so, we have a nice divergence between those two curves. Okay. And what we're able to do then is really look at this curve as sort of an upper bound for structural pavement design. That we can use that as kind of a control distribution when we're designing using Monte Carlo type approaches where we generate strain distributions. We can design, see what we get, and then compare it against a distribution like this, and then make a decision. We need to make it thicker, thinner, or what have you. And so we're in the process actually right now of updating the software to basically allow you to, previously we just had an endurance limit you could put into the program. Now we're actually working on allowing designers to put in an entire distribution and then design for that strain distribution to kind of cover the entire spectrum of strains that they're seeing. The next experiment was intentionally designed to be perpetual by the state of Oklahoma, and they had two questions. One was, do any of these design philosophies really play out in the real world, right? It looks good on paper, we do the simulations, looks good, but what if I take those and actually design a pavement using them? That's number one question. Number two, and maybe the bigger question is, can we afford to build a perpetual pavement? How much thicker does it need to be, and then is it cost effective? So they invested in two sections at our track. N8 was not on the thin side or non-perpetual, and 9 was perpetual, and the difference was essentially 4 inches additional asphalt, non-perpetual to perpetual. We brought in a poor soil for them to build on. We had a really nice foundation material that we used at the test track. They said if we had that, we wouldn't have any problems in Oklahoma. So we found a local borrow pit that had a A76 soil is the technical classification. We called it muck. There's another word for it. Or slop is another good word. Very soft material. And then putting all these properties into our design program, they basically came up with this is non-perpetual, this is perpetual. So N8, the non-perpetual section, had a pretty rough life at our track. It made it through the first 10 million easel, and this is the original construction, okay, of N8. And then at the end of the first 10 million easel, there was enough cracking in the pavement that Oklahoma DOT said we want to do our normal conventional fix for this, which was to mill down about half of the depth, right? And then bring back to the same elevation, so don't add any thickness, just bring it back and put in a paving fabric as well. And that lasted 3.5 million easel out of the 10 that are in our next test cycle. And at that point, we couldn't afford really to do another big fix or do more than one more big fix, and so we decided to kind of think outside the box, and we used some high polymer mix that Kraton manufactures. That's a very fatigue resistant material, and so I'll show you kind of the history of these. But again, the idea being, is it cost effective to build this kind of a pavement versus not building it? So this is showing the roughness of the pavement, and there's two test cycles here, the 06 track and the 09 track, 10 million easel in each. And section N9, there's not really a change in the roughness over time. I mean, it increases a little bit, but it's still below the kind of the cutoff. N8 got very rough, and then we did the first mill and inlay, and then it got over 300 inches per mile. This is where you're having to divert yourself. If you're driving a road that has 300 inches per, you see obstacles in the roadway, and you're swerving to get around them. And then we did the high polymer mill and inlay. It brought it back down and has been very smooth since then. Rutting, again, the perpetual section, it topped out here somewhere about a 1/4 inch, which was good. The non-perpetual had a lot of rutting, and then had rutting again after we did the first mill and inlay, and then it kind of leveled off. What does it look like? Well, this is the non-perpetual section. We've got cones out. That's always a bad sign. And water standing in the section is not draining. It's obviously not performing very well. We've got slippage failure. There's sections that were literally sliding off of our track. It's a dangerous situation to have, and essentially that paving fabric was put in a very fragile location and created a shear plane and basically contributed to that failure, which is a big problem. What was going on down inside the structure? Well, we measure, again, this is longitudinal strain versus mid-depth temperature, and this is section N9, 06. The first test cycle versus the second test cycle. And you can see that, again, as it's aging, it's stiffening. We're seeing a reduction in the strain. We're also seeing a less sensitivity to the change in temperature on the pavement structure, which is, kind of goes along with it aging. What was interesting with N8 was in 06, again, we ran it to the end of the cycle, and then we did a mill and inlay. And you would think if we do a mill and inlay, it's perhaps improved the structural integrity of that structure. We should see maybe the same strain or lower. It actually increased. So what we had done really did not improve. It improved the riding surface for a short time, but it did not, in fact, we had higher strain levels. We didn't really fix the problem. This is showing a lot of FWD data where we've back calculated the layer properties. So this is AC modulus versus date, and this is the 06 track, the 09. The perpetual section, there's scatter in the data, just kind of random variation. but you can kind of see it increasing over time. The non-perpetual section, this is after we reopened to traffic and we had all that kind of cracking going on and shearing. It's dropped quite a lot, and then when we did the mill and inlay, it immediately closed up the variability and improved. It did improve the structural integrity of that section, and you can see it pretty clearly in those modulus values. And this is just looking at measured pavement response in section N8, the non-perpetual, before the high polymer repair, after the high. And you see a reduction in the strain. That goes along with the increase in the modulus, and then also a reduction in the pressures, which is those dark colored bars. So that high polymer mix did have an impact on the structural integrity of that section. How expensive was it? Initial construction was 32% more for that extra 4 inches. But if you look and put together a cash flow diagram, of course we have these other repairs out here, but if you bring it back to net present value, it's actually 26% cheaper to build that perpetual section. So it is economically viable. All right, future challenges. The asphalt industry is really working hard to go green. There's lots of waste streams available that are being worked into mixes as we speak. Reclaimed or recycled asphalt shingles, we're thinking about how to get those safely into a mix that doesn't affect performance, reduces the cost. That's a kind of a tricky business at times. Wrap usage is way up. Again, asphalt's 100% recyclable. You can reuse every bit of it. Some areas have more than others in terms of wrap stockpiles. The state of Virginia, or I guess the Commonwealth, has stockpiles near airports that are so large they have to put beacons on top of them for safety reasons. Warm mix asphalt, ground tire rubber is another thing that's being worked into mixes. Recycling technologies, cold in place recycling. The challenge and kind of where I work in related to these technologies is how do we incorporate all of these different things into these different design systems, right? And that's always a challenge of doing it safely and economically. If you look at the asphalt concrete industry, warm mix asphalt is on the rise pretty dramatically just in the last 4 years or so. Asphalt shingle use is up, wrap is up. It's an industry that is really kind of looking in on itself and identifying areas to basically improve their bottom line but also help the environment. All right, and I think I'm on time. So just a few concluding remarks. Pavement design, pavement thickness design is in transition. I think I've been saying that for the last 10 years or so. It's a long transition. And we're trying to get from these empirical methods to mechanistic-empirical. ME design is much more robust. We're not designing for a change in serviceability. We're designing for cracking. We're designing for rutting. We're designing for distresses in the pavement. We have better traffic, climate, materials characterization, so on. And it's capable of adapting to new conditions. If we think about that old design system and we want to use ground tire rubber, we don't really have a way to rationally incorporate that. In these new systems, we can do that. We measure the properties in the laboratory and we can then incorporate it in the design approach. And I think perpetual pavements are key to a sustainable future. This idea that we build a road and every 10 years we've got to reconstruct it is not viable at all. And going to perpetual is cost effective. And I think coupling perpetual pavement with sustainable materials is a key. And we can load up those layers with recycled materials and so on to achieve a more economical pavement structure. And I'll leave you with this as a nice shot of our test track. And one of the new areas of research that one of our construction professors has gotten into is erosion and sediment control. And so they've got a series of flumes and things, and they're looking at different strategies to control runoff from construction sites and that kind of thing. So there's a lot going on there. Of course, our test track, we've got some other things going on back here related to vehicle and stability control. Our mechanical engineering department has a lot of expensive vehicles. They like to whip around in circles. And so they use this as a test pad. And to the students in the room, some of you may be thinking about graduate school. We love having talented grad students help us at the test track. And these are just a variety of folks I've had the good fortune to work with at the test track. And that's all I've got. Thank you for your attention.
Well, we have time for a few questions.
looking at your statistics from the beginning, you have about 2 million miles of asphalt pavement. If it gets redone every 10 years, I can do this, that's 200,000 miles a year that's getting reworked. Why aren't we collecting the data from those things so that we don't have to try to do everything in terms of test tracks?
We are trying to collect the data from that. There's been a number of studies. There was the long-term pavement performance project that started in the 90s. That was this network of sites all over the country to collect that kind of data. I think one of the challenges is just, even in that project, there was non-uniformity in how the data were collected. And I don't know, John, if you have a comment on it, but it's...
Well, you know, we have...
From a DOT's perspective.
Yeah, I mean, just as far as the, I don't know, if it was up to me, I mean, we'd have way more construction inspectors out there as it is. I mean, we don't have anywhere near the people watching the construction that we used to have. And this is, I mean, it's just unfortunate. We're all paying for this because there's lots of mistakes that are made during construction that would be caught if we just paid people to watch what was going on. So we can't even keep up with what we're actually, and so the idea of collecting more information is a good idea, but we don't have the people to do it right now.
Now, there are some interesting things going on related to that. There's a company in Washington called PEE Systems, and they've developed a series of apps that are supposed to help collect that kind of information. And you know, you're walking along a construction site, you notice something, you snap a picture, tag it, creates a nice record of everything going on that site. But that, I mean, that's within the last year, you know.
David, nice talk. I have a question about your software for designing the perpetual pavement. I was particularly interested in the reduced complexity version of it that you had, that one-page thing. How does that? Is there a significant difference in the output from those two models? If you were to build a pavement that came out from the all bells and whistles versus a very simple one, would you expect to see a significant difference?
You would get the same result, and essentially what we did with the simple version is I had a grad student run thousands of simulations. We kind of set up a little experimental matrix, and so it operates within a fixed set of conditions. So a couple of different load spectra, limited, you know. So it's basically a watered down version of the same software, but so it's limited, right? You're not able to look at a wide set of conditions. It's a very narrow set of conditions, but you do get the same result.
You had shown a map earlier showing states that had won awards for the permanent pavements and ones that didn't. What would you think the main difference is? For example, Colorado had one and Wyoming did not, even though they see similar weather conditions.
Right.
What do you think the main reason?
I think the biggest reason is how the local asphalt association kind of views that program, and even if there isn't a local asphalt association, because it's usually kind of in partnership between the DOT and the local asphalt association, and it's a nomination process. And so some states just don't have an association, or they're not actively promoting perpetual pavements kind of thing. And so I think it's just a matter of not actively searching for them is the big reason. I think they're there. They just haven't been nominated.
Any more questions?
Thanks for your talk. I had a question about the sensing systems you're using for these. So it looks like it's some embedded sensors. So are those wired?
They are wired.
Okay.
Yep.
And then do you do like NDE technology on the track as well, like surface NDE technology?
Like radar and that kind of thing. Yeah.
Array technique.
Yeah. So there are some. We don't own a radar, but we partnering with Virginia DOT. They bring their radar system down and run the track every so often. The other NDT stuff that we do is the FWD testing and so on. And we'll test on top of our gauges to get kind of a direct, link between the measured and theoretical. Yeah.
Any more questions?
One more.
Yep. Yeah, we have time for one more.
This will be quick.
At dinner parties, I almost invariably get a question of something like, why can't we build pavements that don't wear out?
Yeah.
And my classic answer is, well, we could, but it costs too much. Is that still the right answer, or we got something I got something better for me to say to these folks?
I think we are building pavements that don't wear out. I think, you know, the perpetual, I mean, these have been around since the 60s. I think there's examples of it. However, we do have a lot of roads that have worn out and have reached their design life, and a big part of that is just simply when say the interstate system was first designed. You know, I think if you look at the traffic levels that they're seeing now, I mean, it's a like factor of 4 or 5 in terms of what the predictions were versus what they're seeing, and so I think that's a big part of it. But you know, the answer is I think we are designing them to last, and there's a tremendous amount of innovation going on in binder technology, mixed design, the structural. There's tremendous innovation. I mean, I think our pavements are much better than they have ever been as a result of that innovation.
That'll make people feel more comfortable.
Okay. Tell them to support a gas tax increase as well, and we can do lots of exciting things.
On these
The Romans built pavements 2,000 years ago.
That's right.
Still working.
That's right.
Okay, on this positive note, let's join me and thank Professor David Timm
Thank
for
you.
a very
Thank
interesting
you.
presentation.